So we're back to our drawing here of our general launch angle. We've got the initial velocity here, v naught, but now we put numbers on it. The speed is 20 meters per second. So we're going to throw a ball, and when it leaves our hands, it's going to be going 20 meters per second, 20.0 meters per second, at an angle of about 35 degrees above the horizontal. All right? And so what we want to know is some really simple question here. What we want to know is we want to know its position and its velocity at t equals 0.500, 1.00, and 1.50 seconds. We want to know where it is and what its velocity is, not its speed, but its velocity at each one of these times. Now, it turns out the ball is going to hit the ground at about 2.34 seconds. So this is plenty of time. Okay. So this is not going to be after it lands. So we want to know position and velocity. Okay, and so what we have are our equations of motion for projectile motion general angle right here. There they are in all their splendor. And so how are we going to find the position at 0.5 seconds? Well, position just means, you know, X and Y. That's all it means. So all we need to do is solve for X and solve for Y. And we know the time, right? Oh, this should be right there. That should be, those X's should be gone from there like that. Yes. So we know V naught, we know theta. We're given time, so it's easy to find the time. So let's find the time. Let's find X. X is going to be equal to, let's see, 20.0 meters per second, right? This is just equation 2 times cosine of 35 times 0.5, oops, too many zeros. Too many zeros. 0.500 seconds. Just plug those numbers in and you find out that after 1/2 of a second, we are at location x coordinate 8.19 meters. We do the same thing for y, using again equation 2. So this is going to be v naught, which is 20.0 meters per second, times now the sine of 35 times time, which is 0.500 seconds. And again, we're just using this equation 2 here, minus 1/2, 9.81 seconds squared times 0.500 squared. Oops, I left off the unit. That's not always that important, but sometimes it's nice to keep track of them, and I'm doing it here, so I'll keep on doing it. So we're just plugging in for X and Y from equation 2 for X and equation 2 for Y. And so when we do that, we get for Y 4.51 meters. So X is 8.19, Y is 4.51. So here in this picture, X is 8's about here, so the ball is going to be about right here. Okay, so this, I'm not going to draw all of it on the bit, but this X location here is about 8.19, and this height here is about 4.51. This is not quite to scale. The vertical axis is stretched out a little bit. The angle, as you can see, the angle here as I've drawn it is much larger than 35. So the y-axis is stretched out a little bit, but this nonetheless is the answer at, and these are the values at 0.500 seconds. And we can play the same game for the later times. So for the time 1.00 seconds, we get for x and y these numbers. They have both increased. We have x is 16.4 meters, and for y we have 6.57 meters. So both of them have increased. So the second snapshot might be about, it's just before it reaches the top. It turns out it's right about right here. Okay. Now these little hash marks here, don't worry about those. Those I was thinking of using them for something, but I'm not using them. Okay, so I don't want those to distract you. Okay, so the x component has increased. I mean the x, not the component, the x coordinate has increased, and the y coordinate has also increased. And then finally at 1.5 seconds, we get a larger value of x. X is 24.6 meters. And y, after 1.50 seconds, has decreased to 6.17 seconds. So y went up 4.51, 6.57, now it's coming down again. And that's not a big mystery. We're now like about, say, right here. Okay. So this is at it's like mistakes on parade here. Let's see, this should be, there goes my cap, 1.00 seconds. Actually, I'm going to write it up here, One day I'm going to get it right. I'm going to get my head screwed on straight. That'll be a good day. Let's try this again for the third time. 0.500 seconds, 1.00 seconds, and here 1.50 seconds. So those are the locations given to us by these formulas. These formulas describe this motion. Okay. And now we want to find the velocities. Okay, so let's find those. Okay, all we did to find the positions was apply x and y. Equation 2 for x and equation 2 for y. That's all we had to do. Okay? And to find the velocities at the same 3 moments in time, we're going to apply equation which one? You tell me, which equation are we going to apply in order to find the x and y velocities from these equations? That's right, I heard it. I heard it coming through. You all said in unison equation 1, and that's correct. Okay, so we're going to look at equation 1 and use it to determine the velocities. So at t equals half a second, Vx is going to be V naught times cosine theta, right? We're using these equations right here for Vx and Vy. So Vx we're going to have 20.0 meters per second times cosine of 35. And when you do that, you get 16.4 meters per second. That's how fast the ball was moving in the x direction at 1/2 of a second. For Vy, we're going to again apply equation number 1, 20.0 meters per second. Now, sine of 35, because we're in y now, minus 9.81 meters per second squared times 0.5 seconds. And for Vy, you get a slightly smaller number. In fact, it's clearly smaller. You get 6.57 meters per second. So in the x direction, the ball was moving at 16.4 meters per second. In the y direction, it's moving 6.57. I'm sorry, in the x direction is moving 16.4 meters per second. In the y direction, it's moving 6.57 meters per second. These are both positive numbers, which means that at this moment in time, when the ball is right here, it is moving up and to the right. So the velocity vector looks something like that. And it is equal to 16.4 meters per second in the x direction plus 6.57 meters per second in the y-hat direction. Okay, so I should probably just write that over here. We can combine it and say that the total velocity at 1/2 of a second is 16.4 meters per second x-hat in the x direction plus 6.57 meters per second in the y direction. Both components, the x and the y, are both positive, which tells you the ball is moving up and to the right. Up is positive in y, right is positive in x. So this little vector, I'm going to erase the answer right here. That was a little, don't really need that in there. I think it's just going to confuse things in the end. So this little pink vector right there is the one. Up and to the right. I would draw the components, but that would make it kind of, I think, a little bit more confusing than it needs to be. So this is at t equals 0.5 seconds. Now we can do the same thing, apply equations 1 for x and equation 1 for y. We can do the same thing at the later times at t equals 1.00 seconds. We get, they're still both positive. I'm going to get v equals 16.4 meters per second in the x direction, plus, again it's positive, but it is not going as fast in the y direction, 1.66 meters per second in the y direction. Okay, so first thing I want you to notice here, and stick with me, is this. Let me get a different color here. Let's say blue. The x component has not changed. It's moving just as fast in the x direction as it did, at 1 second, as it was moving in the x direction at 1/2 a second. No change in velocity in the x direction. Okay, we'll come back to that in just a moment. That is not accidental. Finally, so let me draw this little vector. So it's still going to be moving to the right, and it's still moving up because the y component is positive, but the y component is not nearly as high as it was before. So that means that the slope of the vector has decreased, and so the vector is now something like this. It has flattened out a little bit. It's not completely horizontal. It's still up and to the right, but it's not as up 1.66 as it used to be, 6.57. Finally, at t equals 1.50 seconds, we have the same x velocity, 16.4 meters per second in the x direction. Now it's minus, we have a negative component, 3.24 meters per second in the y direction. So we have a positive x, which means it's moving to the right, but we have a negative y, which means it's moving not up, but down. So what we have is something like that. So it's moving to the right, so it's positive x, but it's also moving down, so it's negative y. And again, the same thing happens. All three x velocities are the same. And why is this? Why is the x velocity unchanged? Because if you will remember, when we set up projectile motion, we insisted that the acceleration in the x direction was 0. Which means there's no change in the velocity in the x direction. Whatever the initial x velocity is, this is the x velocity for the whole trip. The x component of the velocity does not change, ever. It remains 16.4 until it hits the ground, from the time it leaves your hand to the time it hits the ground. The y component of the velocity starts off large, gets smaller, and then goes negative. It goes negative when it turns over at the top and starts to go down. So from here on out, the y component is going to get more and more negative because the ball is going to be curving closer, steeper and steeper and steeper down towards the earth. Okay. The only acceleration that we worry about is all in the y direction, not the x direction. So all the change in velocity happens in the y direction. No change in velocity happens in the x. Okay? Next up, golf.